So we've just finished quiz 3. You can find all of the quiz dates on the course schedule. Just as a reminder that the course schedule indicates all of the things that we're going to be doing in this semester. So if we go to, I think I've got it here, syllabus and schedule. I handed out, I think, a paper copy of it on the first day of class, but if you've misplaced that, it's posted on Blackboard. And you can see for every date of the semester when we've got quizzes, when we've got homework assignments due, the dates of the class project submissions, and so on. So next on the list of to-do items for you is homework 8, which is due on Friday. And then next week we're going to have that wastewater treatment plant tour. So probably later this week, maybe on Friday, we'll get coordinated and figure out who needs a ride, who's going to be able to drive, and so on. The treatment plant's relatively close. I think it'll only probably take us about 10 minutes to drive down there. And the timing of that's from 1 to 3. Now, our class time is from 1 to 2. I think there are a couple of students who maybe have class from 2 to 3, and so if you're not able to miss the class that day, then that's fine. I'll consider that excused. Just please get in contact with me so that I know what to expect. Today we're going to continue talking about some issues related to water pollution. We're still in Chapter 7 of the book. We're going to talk in more detail about BOD degradation, and then I have an in-class exercise for you as well. Now, this is the in-class exercise that we didn't have time to finish in class on Friday, and looking at what we had to accomplish today, including the quiz and another in-class exercise related to BOD, I thought probably what I just ought to do is give you the solution to this one. I don't think we've got time to work this in-class exercise, and so this is showing the solution. So this is the one where we had a water sample. We're going to run it through a filter and see how much of the solids is retained on the filter. I'll bring this solution up onto the screen here just so that it's recorded into the video as well. So it's got the definitions at the top. By the way, did everybody get a copy of the handout, the in-class exercise? Okay. So this is showing how we define total solids, fixed solids. It's just a matter of weighing the dish when it's clean and nothing on it, weighing the dish after it's been evaporated, weighing the dish after the dish has been burned in a furnace, and so on. So please look over these calculations. I think they're going to lead you straight into some related questions on the homework assignment. But unfortunately, we didn't have time to work through this together live in real time because we need to talk about BOD. Before we get to that, I wanted to briefly introduce a concept known as biomagnification. And maybe some of you have heard about it before in earth science or biology. It's just the idea that there are some chemicals which are going to become increasingly concentrated through the chain of predators eating smaller microorganisms, or the food web. And the idea is that there may be a pollutant in water in a really low concentration, but then the organisms that live in the water, like phytoplankton, are going to be consuming the water, and as they do, whatever the pollutant is may be continuing to accumulate in the tissue of the phytoplankton. So that maybe the concentration of a certain pollutant is very low in water, but it's much higher in the cell mass of the phytoplankton. And then the zooplankton, which eats phytoplankton, is going to have another level of magnification where it's consuming a lot of phytoplankton over its life cycle, and all of that pollutant that's in its food accumulates in its tissue. Ordinarily, this happens with chemicals that are fat soluble. I mean, you can break chemicals down broadly into a lot of different categories, and one of the categories is whether those chemicals dissolve in water or whether they dissolve in fats or whether they dissolve in non-ionic substances like oils and so on. And those that dissolve into fats, you just tend to accumulate in your body because water obviously comes in and out, but things that are dissolved into the fats don't have a way of being excreted as effectively as things that come in dissolved in the water. So in each step of the food web, the exposure is increased because the herring is eating zooplankton that was eating phytoplankton, and every time that pollutant is accumulating in the tissue, so the things that are at the top of the food chain are subject to a lot more exposure to the chemical than is in the water itself. And so DDT is a classic example of this. DDT was a chemical that was very important in preventing malaria in tropical areas. It was used to kill and control mosquitoes. But it also has a really negative effect on the strength of bird eggs. And so it was used until sometime in the mid-1960s or early 70s, where it was phased out in most of the developing world, and it's pretty uncommon, although I think there are still a handful of places where it's used discreetly, maybe quietly, illegally, and so on. But this is just showing how even a very small concentration of DDT in water led to an accumulation in other predator species that was much, much higher. Here you can see the concentration in parts per million, and so in water it's almost undetectable. But the plankton, which lives in water and consumes the water, would, with each mouthful of water, get a little bit of DDT, and over the life cycle of the plankton would accumulate a fair amount of that. And then the minnows that eat plankton have even more in their tissue. The predatory fish that eat minnows have more, and so on and so forth, to where this was one of the primary concerns. Was it was making the shell of endangered birds like the eagle, the bald eagle. Part of the reason why it was threatened is it wasn't able to reproduce successfully because the shell of the eggs was so thin and brittle because of the effect that DDT has. So biomagnification is something that we need to keep in mind as an environmental effect and be sensitive about it when we talk about wastewater treatment, because some of the chemicals that we're trying to remove seem like that they're in a very small quantity and maybe they wouldn't hurt us directly, but they could have an unintended secondary effect. Okay, so now on to biochemical oxygen demand, BOD. Some texts call it just biological oxygen demand. Some call it biochemical oxygen demand. But in either case, what it's talking about is that there are microorganisms which consume food, and as they do, they also utilize oxygen. The two go hand in hand. And so something that isn't necessarily toxic or poisonous, like sugar cubes, which, sugar cubes, if you eat enough of them, it'll rot your teeth, maybe give you diabetes, insulin resistance. And so it's not great to eat sugar cubes, but it's not directly toxic. And we wouldn't normally think of something like sugar as a pollutant, but if you poured a rail car of sugar into the Ohio River, it would just wreak havoc on the environment of the Ohio River, because what would happen is there are bacteria in the river that would start to consume that sugar. They'd break it down, and as they consume the sugar, they're going to reproduce, and they and their offspring would use the dissolved oxygen that's in the water. And so sugar in itself is not directly a pollutant, but the side effect of adding it to the water is it would have a negative consequence because the dissolved oxygen that fish rely on would suddenly be consumed by these quick-acting bacteria. All right, so sugar is not toxic, but it can be a pollutant because if you add it to a stream, the microorganisms will eat the sugar, their cellular respiration will increase, they become more active, they subdivide, they become more numerous, the population expands to the point where they're consuming now an appreciable amount of dissolved oxygen. And the microorganisms are going to be consuming so much dissolved oxygen that we can see what's called a sag, where downstream of where a pollutant is added, that's adding substrate to the water. Substrate is just a fancy word for food. So a substrate is whatever chemical is being used as an energy source by the bacteria in the stream. So if you add a substrate, you're also going to see a need for oxygen to be provided. So BOD, biochemical oxygen demand, is just a way for us to measure what is going to be the consequence of adding certain pollution to water. So if we have a wastewater treatment plant, human waste, by the way, has a biochemical oxygen demand. It's not just sugar that could be a substrate for bacteria, but there are bacteria that break down human waste, animal waste. Anything that's got residual energy in it, there's going to be some sort of bacteria that can capture that energy and make use of it. And so the residual energy that's in human waste is indirectly causing a reduction in the dissolved oxygen in the water. So we have a variety of ways of measuring that reduction in dissolved oxygen. This is just showing in a bottle of water, they have sensors that it's a probe that's measuring how the dissolved oxygen goes down over time. So you put it in a sealed bottle, and then you measure the before of how much dissolved oxygen is in there, in the water, and then you just track it over time to see the bacteria in the water, how quickly they're consuming the dissolved oxygen. Any questions so far about BOD? All right, so let's think about, it's kind of an abstract notion, the idea that what we're worried about is the side effect of the substrate. And so we're measuring, go ahead.
So does the dissolved oxygen problem happen when the pollutant, like the sugar, is gone and they have like nothing else, then they go to it, or is it just automatically a byproduct?
It's as they're eating the sugar, they're also consuming the oxygen. And so at the problem is the worst where there's the most numerous number of bacteria. So you won't see it immediately after the wastewater is discharged into a stream, but it would be like downstream a ways where there's enough time for the bacteria to reproduce that you'd see like the lowest dip in the dissolved oxygen. That's a great question. Any other questions? Okay. Biochemical oxygen demand. So the bacteria demand oxygen. If they're eating food, they demand oxygen. So we're measuring the indirect effect that the substrate has on the environment. So we're adding some sort of an energy source to the environment. The bacteria are using the energy source and consuming oxygen. So, if you were eating carrots versus eating potato chips, obviously because the potato chips are salty, they're going to have a greater water demand. So it's not that the potato chips themselves require water. I mean, they can sit in a bag and they don't require water. But when you eat the chips, now suddenly you get thirsty. So you're going to be drinking water. So it's like a secondary effect. And there'd be maybe less water demand with something like a carrot because it's not salty. If you are playing playing a video game, you're going to be breathing, but you're going to be breathing more if you're actually playing the sport, moving around, running. So the activity has an oxygen demand. And so it's just kind of an analogy to make the point that it's not the pollution itself that is demanding oxygen. It's when it's consumed that the oxygen is being demanded. So, a soccer ball doesn't demand oxygen. It's just introducing a soccer ball in a room of, energetic children is probably going to cause them to run around more. So maybe they're going to be breathing more than they would if they were just sitting comatose with electronic devices. Okay, so here's the oxygen demand curve that shows when you discharge some sort of a waste that contains a substrate. I've mentioned that word now several times, substrate. It's the kind of concept that you should be prepared to explain at a certain point in the future, substrate. So this is showing a graph of dissolved oxygen. So dissolved oxygen is constant, and then downstream of this pollutant source, the dissolved oxygen is going down, it's sagging. and it gets to some minimum, and then it starts to recover again. So this is showing in the dashed line the biochemical oxygen demand. It goes up, and then it's decreasing, and it's back to baseline again. The graph is also showing the types of species that we could expect to see in clean zones, for example. In clean zones, you're going to see fish that have real sensitivity to dissolved oxygen. Certain fish don't mind the sag. You know, carp, garbage fish, they don't mind the sag so much. Catfish probably are fine with low dissolved oxygen, but trout are really sensitive to decreases in dissolved oxygen. And so there's different types of fish. Here it's showing maybe a catfish in the decomposition zone that's able to survive through the oxygen sag. But then in this septic zone, there would be fish absent because there's just simply not enough dissolved oxygen. So what does happen in a septic zone is a lot of mosquito larvae, worms, and insects are growing because there's no fish to control the growth of those in the septic zone. And the other thing is if the dissolved oxygen goes low enough, if there's a complete absence of dissolved oxygen, then there can be breakdown of organic material in the absence of dissolved oxygen can form a lot of really unpleasant smells, hydrogen sulfide, which is in fact toxic. And so septic zones are unpleasant. Like people would notice the smell. And so it's more than just taking habitat away. And obviously if you have a persistent sag, then you could cut off different population of fish. They wouldn't be able to make it through this septic zone, and so they would be isolated, which isn't good. Why do you think the sag is going back up, the oxygen sag? What does that suggest when it begins to recover? Why would the oxygen levels be going back up again? What causes the oxygen to be going back up? Where is it coming from?
Water movement.
Okay. Water movement?
Like air into like rapids or whatever.
Good. It's from the air. The oxygen that's getting back into the river, the source of that oxygen is the atmosphere above the river. So it's a very slow process, this diffusion of atmospheric oxygen back into the water, and it happens quicker if there is turbulence. So, fast-moving water that has rapids and air entrainment, or if, in a lake, if there's air diffusers or some sort of mixing, then that can help the oxygen curve to recover more quickly. But what it suggests when it begins coming back up again is that the rate of air returning into the water is faster than the rate that the oxygen is being consumed. And so we need to think about the mass balance model, that accumulation is in minus out. We've talked about this before in this semester. Accumulation is in minus out. Okay, so accumulation is the concentration of dissolved oxygen. So here, if the concentration of dissolved oxygen is going lower, that means that the consumption of dissolved oxygen is greater than the flow of it in. But then when the dissolved oxygen concentration is returning back to normal, when it's going up, that means that the inflow of dissolved oxygen is less than the rate that it's being consumed. Okay, so BOD is biochemical oxygen demand. It is how much oxygen would actually be used by the bacteria that are in water. We can sometimes do experiments in the lab to test for BOD if we don't want to wait for days and days and days for the bacteria to do their thing. If we just wanted to quickly find out how much oxygen demand there is, we could look at it from a theoretical standpoint and do like a chemical reaction balance. If we knew, for example, the amount of substrate in terms of milligrams per liter, if we added some sugar to the water and we knew how much sugar we added, then we could, using the chemical reactions, find out theoretically how much oxygen would be required to break that organic chemical down all the way, consume it entirely. Another way we could experimentally assess the oxygen demand is by using a strong oxidizer like chromic acid would be something that would oxidize the substrate, would also consume oxygen in the process of doing that. So it's just a quick surrogate for the biochemical oxygen demand. But the difference is that COD, the chemical oxygen demand, is going to use up all of the substrate, whereas the bacteria don't always consume it all. And so COD may overestimate the amount of oxygen demand that's actually present. So biochemical oxygen demand could be lower than the chemical oxygen demand. You know, if you're using a really strong oxidizer, it's going to use up all of the material that can be oxidized, whereas the bacteria at a certain point, when the concentration of sugar gets low enough, they just can't survive on it any longer. Okay, so ultimate BOD is the maximum amount of oxygen that's required to break down all of the organic waste. And the interesting thing is that it may require more oxygen than is in the water to begin with. And so the total amount of oxygen that could be required may be 100 milligrams per liter, whereas the maximum amount of oxygen you can get into water maybe tops out around 20 milligrams per liter. So in wastewater treatment, this is really important because we have to provide a lot of additional oxygen to the wastewater treatment process to allow the bacteria to do their thing. We have to keep re-energizing the oxygen concentrations in the water. So the ultimate demand is how much oxygen is used up if we give it an infinite amount of time and the bacteria are consuming all of the organic waste that they can. So what this is showing is it's a graph of how much oxygen demand there is to begin with, and it's decreasing over time. And so L is the demand for the oxygen, and then that is kind of the mirror image of how much BOD has actually been exerted. So that is like how much oxygen demand has been applied by the bacteria. And this is just a graph of how much is remaining at any given time. So the ultimate oxygen demand is, to break it down all the way, how much oxygen are we going to have to provide to completely exhaust all of the substrate that's available. So L naught is the ultimate oxygen demand, and it's kind of tricky for us to measure that directly because of how long it takes. You know, you can see that it may take even more than a month to break down all of the BOD. And so we have ways of estimating the oxygen demand that don't take the entire 30-day time period. We can kind of extrapolate according to a graphical method that we're going to work through today in the in-class exercise. But this equation, you can see that with the e to the minus kt, that's first order kinetics. We've seen first order kinetics before. So oxygen demand follows the model of when there is a high concentration of BOD, the bacteria are breaking it down at a faster speed than they do when the concentration decreases. The population size is lower. You can't support as many bacteria, so the rate of reaction is slower. So the BOD degradation follows first order kinetics. All right, let me give you the in-class exercise paper for today. What we're going to do is just try out some calculations here related to determining the rate constant. All right, so according to this example, we know the ultimate L naught is 212 milligrams per liter. And at the end of 8 days, we measured that the BOD that had been consumed up to that point was 180.9. So we've got two different time periods. We've got the BOD at time 8, and we've got the ultimate. And so we want to just calculate the rate constant. Now, the rate constant can be expressed in terms of base E, which is associated with the natural log, or in terms of base 10, which is associated with log, Log, instead of Ln. And then the relationship between the two is that the base 10 Log units, we give a capital K to that, and if you see a lowercase k, that means it's the rate constant in base E terms. So let me pause for a moment, give you a time to substitute these values in, and we're going to find out what is the base E rate constant and also the base 10 rate constant. Okay, I wanted to point out something, and that is, if you have, you can see some of the algebra I'm doing here to try and isolate K algebraically. If you've got e to the minus kt power over here on the left-hand side of the equation, if you take the logarithm of both sides, then that is how you get the negative kt out of the exponent of the logarithm. So maybe it's been a while since you did that sort of thing, but the logarithm of e to the minus kt is minus kt. Of course, we have to do the logarithm to the other side as well. So the rate constant here for this one should be 0.24 days, base E. And if we do similar calculations for the base K, capital K, we can either just switch back and forth between the two using the relationship that lowercase k is 2.303 times capital K. So in other words, we have to divide lowercase k by 2.303 to get the rate constant in base 10. Or we could substitute the values into the equation the same way, where we rearrange the equation, try and algebraically isolate k on the left-hand side, put in the minus log of 1 minus the ratio of the BOD after 8 days to the BOD ultimate. Okay, so that's a little bit about these rate constant calculations. And the way that you would measure BOD in the lab is you'd put a volume of that wastewater into a bottle that has a glass stopper that's airtight, and it's all the way, the bottle is full all the way with liquid. You don't want there to be any air bubbles. It's just only liquid. It's an airtight container so that no additional air gets in after the test starts. You just want it to start with a certain amount of dissolved oxygen at the beginning of the test, and then they'd incubate it at a constant temperature and in the dark so that no photosynthesis is causing like the addition of oxygen from algae or something. And then you'd calculate the final dissolved oxygen concentration. You'd measure it usually with like a little probe that senses the DO in water. And so the biochemical oxygen demand would just be the difference between the initial and the final concentration of dissolved oxygen after a certain number of days. So it could be maybe you're measuring after 3 days or after 5 days to find out how much BOD was demanded during that time period. And if you have a really high strength waste, you may need to dilute the wastewater before you perform this test. Because if you have a high strength waste and the initial was 10 milligrams per liter and the final was 0, if you used up all of the oxygen, then you don't know if if it stopped prematurely because it just used up all of the oxygen that was available before it quit. So you can dilute, maybe taking 1 part waste and diluting it so that it is a 1 in 10 mixture. And so you'd find the total sample volume, which would maybe be 300 milliliters. And if you had 30 milliliters of wastewater, adding 270 milliliters of distilled water with no BOD, that would be a way of diluting it and ensuring that the final concentration doesn't go all the way down to 0. So it's a way of assessing the BOD when you have a high strength waste is by using diluting factors. This table shows the amount of oxygen that you could expect to see as a function of temperature. And you can see that the warmer the water is, less dissolved oxygen is in the water when it's in saturation and in equilibrium with the atmosphere. So the concentration goes down as the water gets warmer. All right. The last thing I wanted to show you, and man, we're just always perpetually a couple minutes running out of time. We'll have to pick up with this Thomas graphical method on Wednesday, but what it basically is just a technique for determining the ultimate BOD and not having to wait the full amount of time, which may be a month. So bring this paper with you on Wednesday. We're going to need it especially for the graph on the back side. Yeah?
Can I see the ice problem 1 solution?